distinguished speakers and all the students and audience. Okay, and today is the third day, also the last day for the PolyU 85 anniversary workshop on electrochemical energy storage and conversion towards carbon neutrality. The first speaker today is Professor Xueliang Sun. And Professor Sun is a full professor and a senior Canada research chair, Tier 1, for the development of nanomaterials for clean energy at the University of Western Ontario, Canada. Professor Sun is also a fellow of the Royal Society of Canada and a fellow of the Canadian Academy of Engineering. Professor Sun was elected to the foreign member of the Chinese Academy of Engineering in 2021. Professor Sun received his PhD in materials chemistry at the University of Manchester in 1999. Professor Sun's research is focused on advanced material for energy conversion and storage, including lithium batteries and fuel cells. And he is also many papers, around 600 papers, including many top-tier journals like Nature Energy, Nature Communications, with a citation close to 50,000 times and H index of 115. Professor Sun was named as a highly cited researcher, and he has edited 4 books and published over 20 book chapters and 24 patents. He has given more than 160 plenary keynote and invalid talks, and he received numerous awards such as the Professional Achievement Awards from Cross-Cultural Professional Association of Canada, Award for Research Excellence in Materials Chemistry, winner from Canada Chemistry Society, Award of Merit of the Federation of Chinese Canadian Professionals, Western Helmholtz Prizes, which is the highest research achievement award in the university, and the IBA Battery Technology Award. Professor Sun is the Vice Chairman of the International Academy of Electrochemical Energy Science. He also serves as Editor-in-Chief of the Electrochemical Energy Review. So now let's welcome Professor Sun.
Okay. Can you see a screen?
Yes.
Okay, that's great. Okay, thank you very much, Professor Huang, for your very detailed introduction. Good morning, everyone. I'm Anderson from University of Western Ontario, Canada. So it is a great honor for me to attend this workshop to celebrate 85th University of Hong Kong Polytechnic University. So first of all, I'd like to thank organizers, particularly Professor Haito Huang for his kind invitation. Today, I will talk about all solid-state batteries, from interface design to halide-based solid-state electrolyte. So here, let me see, I try to finish 35 minutes. Okay, let's start with our university, Western University. Actually, that is located in between the Toronto and the Detroit. It's a city in London, 4 hours for each. And also it's very close to the Niagara Falls. Welcome you to visit here on our university. Okay, so let's start with this, the energy. I think that is a lot of speakers talk about the clean energy in the last 2 days. So here is several countries plan to ban the sale of the diesel and petrol cars by certain years. So for example, is Norway, Netherlands is trying to give up the petrol and diesel cars by 2025. Germany and Denmark is 2030, UK and France 2040. Even China is announced 2050. Actually, the number is keep changing because that is the technology develops so quick. For example, BYD this year announced totally give up the petrol car, just to focus on EV cars. So here in this case, if we give up this petrol and diesel cars, so what is alternative? So actually, many speakers talk about fuel cell, hydrogen, and also many speakers talk about the battery related for EV. So our group focus on the materials. Actually, for two devices, one is battery, one is hydrogen fuel cells. So for example, here for battery part, we work on, let me get laser pointer. So we work on the anode cathode materials, work on interface, and also different systems like metal air, lithium sulfur. A couple of years, we focus on solid state batteries. And also we also work on the electrocatalyst, particularly a single item catalyst recent years. So today I just focus on this part, solid state batteries. Why solid state batteries? Some speakers already talked about this. So actually that is two the concerns. One is safety, one is continuing increase energy density. So for example, the people from Toyota might talk about existing one, the energy density next generation, the solid state battery. So solid state battery, they have advantage, but still have a challenge. For example, here, the solid state battery device, you see basically two challenges. One is the interface with anode, the interface with the cathode, and also here solid state electrolyte. For example, here talk about solid state electrolyte with the cathode material. There's a lot of challenges. For example, is mismatch, cracks, stress, and also interdiffusion, chemical, electrochemical reactions. And also many people work on the coating or artificial ICI to control interfacial reactions. And also we need a fast lithium ion transport at the interface. Even at interface, we need different properties, mechanical corrosion properties. So for anode, particularly the lithium metal anode, we have a challenge. For example, bond formation, volume change reactions. So when we talk about solid state electrolyte, so here is a lot of requirements for solid state electrolyte. Basically, we have a polymer-based, oxide-based, and sulfide-based. So each one have advantages and disadvantages. For example, polymer-based, room temperature, ionic conductivity relatively low, and also oxide is ceramic material device integration is a challenge at the interface. Sulfide is very high ionic conductivity, but they have challenge as stability and reactions with the anode cathode. So that's why here is many other groups also try to work on hybrid, or that is try to develop a new type of solid state electrolyte. So our group work on the different the part. For example, we developed the sulfide and the halide interface and also electrode. So for example, we work on the halide-based solid state electrolyte. We also work on the sulfide-based solid state electrolyte. Now we work on the interface with anode and with the cathode. And also electrode part, even that is model cell, pot cell. So today, I just gave two examples. Focus on the interface, particularly with the cathode interface, by using the sulfide-based electrolyte as an example. Second part, I will work on, talk about halide-based solid state electrolyte. So first part, interface. So we're using the sulfide-based electrolyte as example. I know it's many groups work on sulfide-based electrolyte, but we should see the pioneer is Professor Kino. He worked on this for many years. There are several generations of sulfide-based electrolyte. Here I talk about the advantage, very high ionic conductivity, but they have a challenge, air stability and also reactions with the cathode anode. So that's why here all group work on this material from synthesize, for example, is try to control air stability and also control the structure, maintain good ionic conductivity. And also anode cathode interface control, particularly here when we synthesize the doping, for example, fluoride, or we're using the MLD, ALD protein. And also, we also demonstrate the system like lithium sulfur, lithium selenium system. But now I just focus on interface with the cathode. So talk about the interface. We know it's artificial interface is the good approach. What is ideal interface? Actually, we need an ultra-thin uniform interface. So at that interface, they have different properties. For example, control ionic conductivity, electronic conductivity, and even mechanical corrosion properties, toughness. So that's why here the different groups work on different approach to have an artificial interface. For example, CVD, PVD, or pseudo method. But we can see that none of them can get ultra uniform at nanoscale. But the ALD and MLD is the good approach to get that nanoscale ultra uniform artificial interface. So our group work on this one many years to try to develop the ALD or molecular deposition method. For example, if you talk about lithium metal, we need control artificial interface. For example, we're using ALD, MLD hybrid to control it. Recently, we're also using a gradient, the coating to protect the lithium metal. And also we can control the electronic conductivity of the interface. So from here, we can see ALD, MLD play a very important role as an artificial interface. So what difference between the atomic layer deposition and the molecular deposition? So actually, I talked about this before. Is generally ALD for inorganic material like metal oxide. And the molecular deposition generally for organic or organic with inorganic hybrid. So that in this way, we can control mechanical property as an interfacial interface. So what kind of interface material is ideal? Actually, we should thank Professor Yves Moore from the University of Maryland. They're using calculation to tell us what kind of material is ideal as interface with the cathode and with the anode. For example, with the cathode, they see the electrochemical window is this kind of material is good. So that's why our group using ALD to synthesize this kind of material as an interface in solid state batteries. And also, they also work on molecular deposition as well. So here, talk about the cathode interface. So we know at the cathode, they have a solid state electrolyte with a cathode material or other interface. So for example, cathode with a solid state electrolyte interface, this part, actually a lot of things we need to do. One is we should understand what happened at this interface. And also the electrodes, the engineering, how important. And also the coating, how to prevent sulfide-based electrolyte reactions. And also how is ionic conductivity important at the interface. and also the coating, different coatings, what is the more effective. And also even the single crystal or molycrystal, polycrystalline, which one is better in solid state batteries, or even solid material, the surface, how clean is the clean surface, how important. So all the things we need to address at the cathode material interface. So here, let me give an example. The first one talk about understanding what happened at the interface. So we're using operando zines to study the cathode material, cathode interface. So we pick up LGPS and MC811. We try to understand some questions. For example, why is we have a big irreversible capacity feed, and also what happened at the interface, particularly without ARD coating, what happened. So in this case, we need a similar battery to test without coating and with coating. So from here, we can see the big difference. What happened at the interface? We're using zines, in situ zine study. During the this chart, we found some new compounds corresponding to lithium sulfide. And also we found nickel, the key age shift, indicating is nickel reduced. This is without ARD coating, some reactions. With ARD coating, you can see this kind of the reactions. So we also try to understand what happened at the near surface. We're using high-resolution TM. We see that here is 12 nanometers at the surface. We found structure change, phase transition from layer structure to rose salt structure at about 10 nanometer speed. So in this case, we see that we do have a lot of reactions we need to address. So next example, we try to using the ARD synthesize lithium phosphate as a coating on this interface, particularly compare liquid system and the solid, what difference. So we have one study, have a collaboration with PNL, with Dr. Jigong Zhou's group and Dr. Chungming Wang's group. In that moment, we try to understand 811. We have a cracks along the green boundary. So we try to address this challenge by have a coating, ARD coating first. After coating, we try to have a simple annealing to put this coating material into the green boundary to try to prevent the cracks along the green boundary. So we using the ARD synthesize lithium phosphate. The coating on the particle, we see that is phosphate agonal. The signal here, after a simple annealing is penetrated inside. If you look at details and green boundary here, we still have the phosphate signal along the green boundary. So that means that here is a material, coating material penetrate into the green boundary. So we test the performance, we found, yes, with the coating annealing, that is the cycling rotation is much better from almost 79% increase to 91% after 200 cycles. Higher temperature is a bigger difference. We also try to understand what happened. Actually, without coating annealing, we see there's a liquid-based electrolyte penetrate inside. We have a fluorine signal, carbon signal from liquid electrolyte. But with coating and annealing, you cannot find that signal fluorine carbon inside. Also from a higher resolution TM, you can see without coating, maintain very good structure. After 200 cycles without coating, you see that is phase change. If we have a coating annealing, you see maintain very good structure. So from this example indicating a coating with a simple annealing can address three challenges at the same time. One is to prevent cracks and also prevent erections and also prevent phase transition at the same time. So after the liquid system, we try to know if we want to use the sulfide-based solid state system, what difference? Even we're using the similar coating or simple annealing. So we pick up LGPS as an example to work on that. So we use the same procedure coating with the annealing. We found this material solid state system not that good. Is without coating it cannot be very good. With coating, still have a challenge. It's from 92% citation after 200 cycles, now it's 66% after 100 cycles. So that means the bigger challenge is solid state electrolyte. So we can see this part actually with the sulfide based, after annealing material penetrate inside, but the coating here is not continue on the surface. So we try to see if I have an extra coating on top, can we improve performance? Actually, yes. After we have additional coating on the top, this we can increase to the 78%. Readability is better too. But still have a challenge. For example, we have a cross section we found without coating annealing, we have a big cracks on 811. With the coating annealing, with the coating again, you can see it is better. But still, you have some reactions. Without coating, they have reactions from XPS. With the coating annealing, with the coating again, is can significant prevent the reactions. So next example, we try to answer another question. Interface. Our interface ionic connectivity at the interface, how important? Is low ionic connectivity or high? Is how high is good as an interface? So in order to answer this question, we have an interface layer is near lithium, neodymium, titanium oxide is 5 nanometers. Is in order to control ionic activity, we have a low temperature annealing is control the different ionic connectivities when we maintain the same thickness. So after we testing performance, interestingly, we found a big difference. With the highest ionic connectivity at the interface, we see that it's maintain much higher capacity. With the lower ionic connectivity, its capacity much lower. So that indicating this barrier, lithium transport at interface, so important, even that is rate capability. So from this study, we know that here we do need really good ionic connectivity at the interface. Also, we next story, we try to compare a single crystal and the polycrystalline. We try is good in solid state battery. Actually, here we know is polycrystalline for liquid electrolyte is good because easy to penetrate inside. But for solid state, it's hard to penetrate inside. That's why here we assume a single crystal is better. So after testing, yes. Let's try, for example, after 150 cycles, rotation is a big difference, 61% and 94% difference. Replicability also quite big difference. So let me give a summary on this part. Actually, give 3 examples. One is in situ. This study try to understand what happened at interface. Another one is coating is important for sulfide-based electrolyte. And also the ionic connectivity at the interface is very important for the lithium transport. Also, I gave one example, single crystal is also important. So for sulfide-based electrolyte, many people work on that. We try to continue increase ionic connectivity from 10 to minus 2 to 10 times higher in the electro level. And also air stability also important for synthesize solid state electrolyte. For battery level, we need to control interface. As I mentioned here is the electrode interface very important. So actually, when we talk about air stability, we also work on that. We dope tyramine in LGPS. We found not only increase ionic connectivity, but also increase air stability. with this doping, we can reduce H2S a lot. Also, we can dope other elements to try to increase air stability. Yeah, this part, actually, I mentioned ARD, MRD a lot. So here our group dedicates this part many years. From beginning light scale, now actually they can produce a big amount. 20 pounds per day is that device available. And also for electrodes, continue process row to row from ARD, MRD also available. Okay, so I finished the first part. Let me using maybe 10 minutes finish this part or less. Halide-based electrolyte. Actually, we should thank Panasonic and the collaborator. They found the new system, lithium chloride with very high ionic conductivity and also air stability as well. Without coating, they demonstrate its battery works, particularly it's better than sulfide. So the structure is they have a lithium ions aggregation mechanism, particularly from architecture to tetrahedral, this structure. That's why it's very high ionic activity. So we have a summary on this part. Actually, for many years, people increase ionic activity from 10 to -7 to 10 to -3 using that is 90 years. So here, one of the group, Dr. Kano, make a great contribution on this part. So here I mentioned Panasonic work and other group as well. All group are working on that first report 2019. Later on is other group working on that a lot. So Germany group, Dr. Linda Nata group. And also 2022 is more group getting involved. So this part our group work on synthesis, structure control, stability application. For example, we try to develop a different approach to synthesize, control the structure, have a good ionic conductivity and air stability, and also the use it for different systems. So I give an example, lithium indium chloride. So we work on that because we found this first report many years ago is ionic conductivity very low. And at 200 degrees C, they have ionic conductivity. Room temperature, they don't have a good ionic conductivity. We're just using ball milling found a simple process that we get 10 to -3 ionic conductivity. Also, air stability is very stable. We demonstrate the battery is working and also stable with the cathode without coating. After this ball milling method, we also try to have a mass production. We develop a solution method, liquid. So we're just using very simple process put together. After annealing, we get a room temperature, very high ionic conductivity. So interestingly, we put back in the water after heating, maintain the same ionic conductivity. When we work on that in the beginning, we have a small amount. Later on, we have several 10 kilograms level mass production. And we demonstrate if batteries works. But again, we need to protect anode part. So later on, we work on lithium scandium chloride, have a higher ionic conductivity. We have a collaboration with Professor Yuve group to understand. Also, this system is interesting with the lithium metal also is stable. In the beginning, is some reaction, later on it's very stable. And demonstrate the battery model cells works. Recently, we work on another approach. The reason here, lithium indium chloride is working using very simple process, but we cannot synthesize other systems. The reason is when we synthesize the other system using simple liquid method, they have impurities. Is that impurities inside decrease ionic conductivity. And then we found how to remove these impurities from this ammonia treatment. We can remove it. Finally, we can synthesize a lot of systems using this solution method with ammonia treatment. We can demonstrate the battery performance. Also, we understand the reason also related to microstrain in the structure is resulting in very high ionic connectivity. So last part, I tried to have some future work. Actually, this area relatively new, still a lot of things to do. We have a summary here talking about this halide-based electrolyte. In earlier years, very low ionic connectivity. Recent years, we can increase ionic connectivity, but still have a room. From now to sulfide-based, we have a still big room we can work on. So how to get higher ionic connectivity, increase 10 times ionic connectivity? We think about probes. So ionic transport important. They have a different approach. For example, control structure. An ionic framework. Recently we work on different systems. We can control structure, maintain very good ionic connectivity. And also the cation arrangement, talk about disorder and order structure, also important. For example, Germany group, Japan group work on that. And the defects, chemistry, doping, vacancy, defects, strength control, you can continue work on the ionic connectivity. And also here, diffusion mechanism understanding. For example, the example from Howard to control the structure. So in this case, we can work on a different approach, continue increase ionic connectivity. Last part, I think not only solid state electrolyte, and also we need to work on the electrode. Very thin solid state electrode, very important for high energy density. So we have a summary. You can using different approach to have very thin the membrane down to about 20 micrometers. Using this way, you can increase energy density of solid state battery. We demonstrate you have a port cell. In the end, talk about sulfide-based electrolyte, actually still many challenges. For example, when we talk about green color is the highlight. This one is a sulfide, red one. The sulfide very high ionic connectivity, but they have a challenge, air stability reactions. But the highlight, you can see without coating with the cathode stable. And also air stable is really good. Only thing that here is with anode lithium metal, both of them we need to address. So how to address this part? Actually, from Professor Ivan's calculation, we know how to do it. Currently, we work on chloride system. You can see the electrochemical window. This one is it's not close to 0 volt. So that's why it's not stable with lithium metal. But other system, fluoride, is much better. So that's why here we need to continue have a wider electrochemical window. One is a high voltage with a cathode, one is the lower voltage with the lithium metal. Okay, so let me stop here. I think today I talked about two parts. One is interface, particularly talk about ALD, NLD as artificial interface layer. And also I gave introduction, the halide-based electrolyte. So that is my group members. Thankfully, very hard to be working, and also collaborators. Prof, the former members also make contributions. A lot of collaborators, and also last slides I mentioned here. Also thank you all for your support for the journal. Is Professor Jijin Zhang, and also editors. for this electrochemical energy views. Many contributors, all here including Professor Haikal Huang's view, gave us support. This year is a new impact factor is 32. I'd like to see the continue get your support. I think that's everyone. So that's why it's in the end very quick. Okay, thank you very much for your attention.
Okay, thank Professor Sen for such a wonderful talk. So now we have time for a few questions. So we would like to ask questions from the audience. Any questions? You can either type in the chat room or just unmute yourself to ask your question. Maybe I start to ask the first question. And in your talk, you the first part of your talk, you use ALD, right, to put a coating on the cathode particles. So, you know, for a battery in using liquid electrolyte, there is a tendency to use large single crystal particles, right? But in solid state battery, if you using your ALD technology, do you imply that you don't have to use very large single crystal? You can use relatively smaller primary particles and then coat it with ALDs, and they can also provide a good performance.
Yes. So actually, here talk about ALD process. Yeah, when we talk about the single crystal or polycrystalline, the ALD advantage of ALD, we can deposit coating uniformly in polycrystalline everywhere. We should see generally that is depends on the mechanism of ALD, because here, yeah, give an example here. So because based on the mechanism ALD, that is diffusion, and also it depends on the function group on the surface. So that's why here is this process you can deposit everywhere, even the channel or holes. So that's why it's for polycrystalline. We should see they can deposit everywhere. Even the powder now, I mentioned here is mass production now is available for 20 tons per day production. Is also is available now for uniform deposition. The reason here they combine chemical reaction process, fluidized back. During the ALD coating, they have fluidized powder, allow the powder is flow. That's why they can produce big amount. So in general, that's yes, is ALD, they can deposit very uniform everywhere.
Okay, so is there any question from the audience? If no, let's thank Professor Sen once again for your wonderful talk.